Before we get into the main part of today's lesson, I want to talk about a technique for dealing with vectors that's going to be really important and necessary for us to use from here on in. So before I get into the vector part of this technique, I want to kind of lay some groundwork for it. And to help convince you that it is useful and that it works, I want to talk about what it would be like if we applied the same technique for numbers. Kind of one of my themes throughout this part of the course is all these things we do with vectors that might seem weird actually aren't, because we can do the same things with numbers. So I want you to think of a number between 1 and 9 that you really dislike. Let's say maybe it's the number 7. A lot of students, I find, for whatever reason, don't like the number 7. So let's say you dislike the number 7, you hate working with the number 7. When you see the number 7, it gives you a panic attack, and math would just be easier for you if you never had to deal with the number 7. So let's say I asked you to do a problem like this. I'll write it down in the example area. 7 times 2. Well, if you looked at this problem, you'd see the 7, you'd have your panic attack, you wouldn't be able to solve it. One technique you could use is, as soon as you saw this problem, before you have any time to focus on the number 7, you could sort of rewrite it really quickly. And you could rewrite that 7 by replacing it with two numbers that add to make it. So what are two numbers that add to make 7? Well, 3 and 4 are two of those. So I can replace my 7 with 3 plus 4. And then I could leave the rest of the problem the same. So rather than doing the top line, 7 times 2, and getting 14, I could do the next line. I could go 3 times 2, and that'll give me 6. And then 4 times 2, and that'll give me 8. And then the 6 plus the 8 gets me to the same result. It gets me to 14. And when I use this approach here, I never had to work with the number 7. As soon as I saw that 7, I quickly replaced it with a 3 plus 4, two numbers that add to make it, and then I never had to deal with it again. So that technique we can use with vectors as well. And the idea is this. Any vector can be replaced with two vectors that add to make it. Any vector can be replaced with two vectors that add to make it. We have a special name for these two vectors. They are called components. So let me give you sort of a better example of this. Rather than using those numbers, let's draw a vector like this one. So let's say I take this, let's draw one like here. There's a vector. And you might not love the look of that vector because it's not super clear which direction it's going. It's not going up, it's not going down, it's not going left, it's not going right. Those directions are easy to work with. This one's kind of going on an angle. So much like you may dislike the number 7, you may dislike this vector. So what I can do is I can replace the vector with two vectors that add to make it. So I could replace it with one vector that goes like this, and with one vector that goes like that. So these two green vectors, notice they're added head to tail. This guy plus this guy equals the blue guy, just like 3 plus 4 equals 7. So these two green vectors are called my components. Now, as I've done in this picture, what we normally do is we choose one horizontal component. That's this guy here. And we call that the X component. And we choose one vertical component, this guy here, and we call that the Y component. So I'll even label them on my diagram. Here's my X component, and here's my Y component. Okay. Let's do one more example. So let's say I have a vector that's going like this. Again, that direction isn't super clear. It's not up, it's not down, it's not left, it's not right, so I might not like that vector, much like I might not like the number 7, so I can replace it by two vectors that add to make it. And I can choose one that goes up like that, and one that goes like that. This guy being my Y component, and this guy being my X component. And so now that I have these components, just like I was able to ignore my number 7 and just focus on the 3 and the 4, I can now ignore this blue vector and just work with these green ones from here on in. And that's what we'll do later on in this lesson once we get there. Okay, so with that idea of vectors and components in the background, let's talk about the real topic of this lesson, 2D projectiles. So a projectile is an object that moves through the air where the only force acting on it is gravity. And we've actually solved problems with projectiles already. Any time you've solved a problem where an object has been dropped and has fallen to the ground, or an object has been thrown straight up in the air and come back down, those are projectiles. As soon as they leave your hand and before they hit the ground, they are moving through the air, and the only force acting on them is gravity. That's what makes a projectile. But all those projectiles we looked at were one-dimensional projectiles. They moved in a straight line, up, down. Sometimes they moved up, sometimes they've moved down, sometimes they moved up and then down, but they're always moving along that straight up-down line, that one dimension. In this lesson, we're going to look at 2D projectiles. So projectiles that move not just in the up-down direction, but also in the left-right direction. So they're moving in 2 dimensions. And so let's start by drawing out a trajectory, so the path that a 2D projectile might follow, and we'll imagine one that has a horizontal initial velocity. So to figure out what I mean when I say horizontal initial velocity, one thing you can do is imagine taking a ball and imagine throwing it. And when you aim it, you're going to aim directly horizontal. You're not going to point down towards the ground. You're not going to point up towards the sky. You're going to aim it completely horizontal. So if there was no gravity, the ball would just continue on at the same height above the ground, not getting any closer or further from the ground. That's what I mean when I say horizontal initial velocity. Now, you know that as soon as you let go of that ball, gravity is going to start pulling on it, and it will get pulled towards the ground and eventually make it there. But initially, right at that first instant, as your hand lets go of the ball and it enters the air, it'll be aimed, it'll be going in the horizontal direction. even if a half second later it started to move down towards the ground, its initial velocity is horizontal. Another way you can imagine this is imagine you roll a ball along a table really fast. When it gets to the end of the table, it'll continue to shoot out for a bit, but it'll also fall down towards the ground. Because the table is horizontal, the ball is initially moving horizontally along the table as it enters the air, and then once gravity has some time to act on it, it starts to sort of curve down towards the ground. So the trajectory that one of these balls would take, whether I've thrown it and aimed it horizontally or whether I've rolled it off a table, it'll follow a trajectory that's sort of like this. Okay, so at the beginning here, it's moving horizontally, and as time goes by, gravity starts to pull it down, and it starts to bend down towards the ground. So the next thing I'm asked to do here is to show the velocity at several points. So I'm going to do that with my blue pen here. At this point here, the very first point, the instant where I let go of the ball, remember its velocity is horizontal. So if I were to draw its velocity as an arrow, it would look like that. That's what my velocity looks right here at this point, the instant I let go of the ball. Now a little bit later, maybe over here, gravity has had some time to kind of pull down on the ball. It's starting to have some downward movement. So my velocity looks maybe a little bit more like this. Let me just make sure I'm kind of measuring these guys approximately right here. Yeah. And then a little bit later, maybe down here, this guy will have yet another velocity. Which I'm going to draw. Just let me measure this out because I want to make sure I get this sort of scale right. I'm going to draw this velocity is going down in this direction. Like that. Okay, oh, I curved this one a little bit. Let me fix that vector. Okay, so this shows the velocity of my ball at 3 different points. That point, at that point, and that point. Now, most of these velocities are kind of at awkward angles. They're not going, just left, right, or just up, down. They've got a bit of a slant to them, which makes them, much like the number 7, a bit annoying to work with. So I'm also going to include the x and y components of these velocities. I'll do that in green here. So this velocity has an x component and a y component. And this velocity has an x component and a y component. So what you might notice about the velocities themselves, there's a few things that are changing. Like compare these 3 blue vectors. One thing that's changing is the length of the vector is getting slightly longer every time. The other thing that's changing is the direction. It's getting more and more tilted, more and more slanted. So there's a few things going on here, and that can be sort of hard to keep in your mind all at once, which is why we like to think about these components instead. So let's just look at the x components, and let's see what's happening with them. There's an x component. There's an x component. And this first guy, I didn't really split it into components because there was sort of no need. It is basically its own x component. It is already in the x direction, so I don't have to draw a component of it that's in the x direction. So these three guys I've highlighted, those are my x components. And if I've drawn this correctly, what you'll see is that they're all the same length. So the portion of this ball's velocity that's moving horizontally, the portion that's moving in the x direction, represented by these three arrows, is always the same. The reason for that is because there's no force in the horizontal direction on this ball. There's no force pushing it left or pushing it right after it's been thrown and before it hits the ground. So there's no reason for it to accelerate left or right. So whatever velocity it has in the left-right direction, it just keeps. And that's why these three components are all exactly the same. So now let's look at the y components. Well, this guy has no y component at all. It is not moving up or down in the slightest. This guy has a little y component, and this guy has a much bigger one. So unlike the x components that were all staying the same, the y components sort of start at 0 and get bigger and bigger as we go. And that kind of makes sense because just like there was no force in the x direction, meaning there was no reason for the x components to change their direction, to change their magnitude, there is a force in the y direction, and that's gravity. Gravity is pulling this thing down. So we've solved a lot of problems where I have a ball and I hold it up and I drop it. And we know that its initial velocity is 0, and as time goes by, it gets more and more downward velocity. Well, that's exactly what's happening to the y components here. The instant I let go of it, the y component of its initial velocity is 0, and as time goes by, the y component gets bigger and bigger. Its initial velocity gets more and more negative. So the advantage here is when we look at the components, it's a little easier to understand what's going on in y than if we look at the full blue vectors themselves. In the x direction, I see the components are always the same. That makes sense because there's nothing speeding it up or slowing down in that direction. And in the y direction, the y component starts at 0, and then it gets bigger and bigger as gravity has time to work. That seems to make sense. If I look at the blue vectors, I'm just like, well, I think it's getting a little bit bigger all the time, but it's always changing direction. It's a little harder to kind of figure out what's going on and why. So these notes I wrote about, or I mentioned about the components are important. Let's write those down. So the x components are all the same because there's no horizontal force to speed up or slow down the ball. These y components, on the other hand, are getting bigger and bigger. And that's because there is a force, gravity, acting in the vertical direction. Okay. So now that we kind of have a bit of an understanding of components and how to work with them and why they might be useful, let's look at an actual problem we might try and solve about a 2D projectile. And I'll walk you through the problem-solving technique that I like to use. So here's the example. A ball is thrown horizontally at 14 meters per second from on top of a 12-meter high building. Okay, let's draw this out. Here's my building, and there's the ground. Building is 12 meters high. Ball is sort of thrown from up here, and the ball sort of does that. Hits the ground over there. And its initial velocity, I can draw that out just like we did before. It's 14 meters per second. Okay, so after drawing a diagram, the first thing I like to do in any kinematics problem is identify initial and final. So just like we're used to doing in 1D problems, let's do the same here. I'm going to call this point the instant where the ball is released, and the instant where it sort of enters the air is my initial. And final is the instant, like just before or just as it first touches the ground. So it hasn't stopped yet. It's still got a ton of speed, and it's hitting the ground with that speed. And after final, the ground will compress, the ball will compress, and they will kind of squish, and it'll slow down and come to a stop. So from initial to final, there is no force acting on the ball. The hand is no longer touching it. The ground has not yet touched it. It is just flying through the air with only the force of gravity acting on it between these 2 points. Okay, so this looks very similar to the sort of problems we're used to solving in 1D. I'm given a VI, I'm given a D, I'm asked for a delta T. I can figure out that there's an acceleration that's probably 9.8 meters per second squared down. Seems a lot like a 1D kinematics problem. The only exception is that we know the ball is not going to be moving in a straight line. It's going to be following this curved path. It's going to have up-down motion and left-right motion. And as we kind of looked at in the previous page, when I have vectors that are moving both up, down, and left, right, a great tactic is to look at the x and y parts of those vectors separately. So let's do that here with our problem. Let's look at the x and y parts of this problem separately. So this is the horizontal part, or the x part, and this side will be the vertical part, or the y part. And look at, like we would do with a 1D problem, I have a VF, a VI, an A, D, and a T. Okay, so let's try and fill some stuff in. And the trick here is not only do I have to decide if something fits, if I have a number, and not only do I have to decide whether it's VF or VI or A or D, I also have to decide now whether it fits on the horizontal side or on the vertical side. So let's look at what's given to me in the problem. The ball's thrown at horizontally at 14 meters per second. That's this guy. Well, that is at the beginning of my problem. So that's initial. It's in meters per second, so it's a velocity. So that's going to be an initial velocity. So it's either going to go here or here. Now, is that initial velocity in the horizontal direction or in the vertical direction? Well, looking at my diagram, we see that this 14 meters per second is horizontal. Also, it tells us in the question it's horizontally. So that 14 meters per second is going to go in for VI in the x direction. And it's going to the right, so it's going to put it as positive. Now, what else do we have here? Well, while we're talking about VI, this is the horizontal component of its velocity at the beginning, but what is the vertical component of its velocity? This tells me how fast the ball is going left-right, but at this moment, how fast is the ball going up-down? Well, you might recall on the previous page, when we looked over here, we said that this guy had a y component of 0. At that very instant the ball is released, it's not moving up or down at all. Its y component is 0. We have the exact same situation here. So because its movement is all horizontal, not up or down in the slightest, that means the up-down part is 0. There's a reason why I'm keeping this 14 is in blue and everything else is in green. I'll get to that in a moment. Okay, so what else do we know about this? Oh, yes. We're told that it's a 12-meter high building. Okay, so based on those units, that sounds like that's maybe a displacement. Is it going to be x or y? Let's think about it. So displacement, remember, is a straight arrow from start to finish. So I can draw the displacement out on this diagram. Here's my start. There's where I finish. That red line is my displacement. And what that problem with that red line is it's at an angle. It's hard to describe its direction because it's going kind of to the right, which makes me want to say positive, but it's also going kind of down, which makes me want to say negative. What do I do with annoying vectors whose direction I don't like? I split them into components. So I'm going to replace that displacement with its y component and its x component. And so this y component of displacement is what goes here for displacement on the y side. And this x component of displacement goes here for displacement on the x side. So that 12 meters we were given, that is the length of the y side of my displacement. And because this is going down this red arrow, that means my displacement is going to be negative 12. My ball is ending up lower than where it started. So for my y displacement, I'm going to put a negative 12 meters. Okay, what else would we use in this problem? Well, that's kind of all the numbers we've been given, right? There's the 14, there's the 12. We used all those. There's one more thing I know in this problem, and that's because it's a projectile. Acceleration should be negative 9.8 or 9.8 meters per second squared down. Remember, if we check our three things, we say, is this ball close to the surface of the Earth? Yes. Is air resistance going to be negligible for this type of object? Yes. And is gravity the only force acting on it? Yes. because those three things are true, the acceleration will be 9.8 meters per second squared down. So, where does that go? Over here on the x side or over here on the y side? Well, I just said the acceleration was in the direction down, so that means it's going to fit on this y side. And down means negative, so negative 9.8 meters per second squared. That is my acceleration in the y direction. Now, what about the x direction for the acceleration? We kind of said over here that in the x direction, there was no horizontal force to speed up or slow down the ball. Right? All these x components were exactly the same. So if in the x direction it's not speeding up and it's not slowing down, that means it has an acceleration of 0. So in the x direction over here for acceleration, we can write 0. Okay, so we've got a fair bit of information now. There's one more thing I want to point out, and that is over here in the x direction. If this thing starts at 14 meters per second, and then it doesn't speed up or slow down, that means over here at the end, the x component of its velocity is going to still be 14 meters per second. And that jives with what we were saying on this previous page, right? If this was 14 meters per second, then this would be 14 meters per second, and this would be 14 meters per second. The x component always stays the same. It starts at 14 meters per second, and it ends at 14 meters per second because it's not speeding up or slowing down. And now the last thing I want to kind of talk about here is the time. Because that's what we're being asked to solve for in part A. How long is the ball in the air for? So are we being asked to find the x time or the y time, the horizontal time or the vertical time? And what does that even mean? Well, one way I like to think about it is this. Imagine you're being asked to time the ball from here to here. But imagine you're being asked to find specifically the horizontal time. So you're not looking at all at the ball's movement up, down. You don't care if it's moving up, if it's moving down, or if it's moving neither. You basically treat this as if there's a starting line here and a finish line here. And you're just looking for the time it takes the ball to get from one of those lines to the next, regardless of whether it goes up or down in between. So imagine you time that, you get a certain number. Then let's say we have another person who's in charge of finding the time in the vertical direction. So they're going to imagine that the start line is here and the finish line is here. And they're going to not worry about the ball moving left or right at all. They're just going to time how long it takes from the time it leaves this start line to the time it gets to this finish line. As you might be able to see, both of those people, my horizontal timer and my vertical timer, are both going to start their stopwatches at this moment, the instant the ball is released. And they're both going to stop their stopwatches at this moment, the moment the ball hits the ground and reaches this final distance away from the building. So even though they're kind of looking for different things, you could say, they're both going to get the exact same time. So this time is going to be the same on both sides. Another reason we can kind of justify that, saying that, is the reason a lot of these things had different answers on the left and right, like VF was different, VI was different, A is different, D is probably going to be different, is because these are all vectors. Those things all have vector hats. And a vector can be split into components, like we were doing here. It has an x part and a y part. But time is not a vector. Time, and that's why I write it here with no vector hat, time is just a number. A number doesn't have an x and a y component. So it might even make sense not to write time on the x and on the y side, but to maybe just write like time once in the middle. Because it's not a vector, it doesn't have components, so it can't be sorted into one side of this grid. That's why time is just time, and it doesn't matter if I'm talking horizontal or vertical. It's just one number on either side. Now, the reason I've chosen green for some of these numbers and blue for others is because the stuff in green is going to be the same for every single problem you do that's a projectile with horizontal initial velocity, right? Gravity is always going to be 9.8 meters per second squared down, so it's always going to be on this side, and there's always going to be no horizontal component to it. If you're releasing the ball with an initial velocity that is horizontal, then it won't be going initially up or down at all, and VI in the y direction will always be 0. Time is never going to be a vector, so these two will always be the same. And the other thing I want to point out is that because this acceleration is 0, VI and VF on this side will always be the same. So this stuff I've written in green is going to be the same for every problem you do in this section of the course. The stuff in blue are numbers that were unique to this specific example that we're working on. Okay, so now that we've set things up, let's think about how we can solve this. So I'm being asked how long the ball is in the air for, which means I want to find t. I can find this on either side because I know they're going to be the same. So which side do I want to use, the horizontal side or the vertical side, to find t? Well, it seems I've kind of got equal information on both. I know 3 things on this side, I know 3 things on this side. The equation I end up using might be a bit different in each situation, but it shouldn't be a big deal. However, the horizontal side would actually be a bad choice at this point in the game. If you go and actually try to find an equation for this, you say, okay, I want an equation that has t, so I can find it, and it has to not have d. So you think maybe our first of the big 3, VF equals VI plus AT. But if you solve that for t, you end up just getting t equals 0 divided by 0, which any calculator will tell you is undefined. It's not a number. It's impossible to turn that into a number. So the left side, it appears, can't actually give me a number for t. The reason for that is this. Even though it looks like we know 3 pieces of information, we don't. Sure, we know the initial velocity is 14, and we know it's not accelerating. But if we know those 2, we automatically know that the final velocity has to be 14. So the problem telling me that it's 14 isn't really extra information. That's just the same 2 pieces of information I already knew. This sort of happens when acceleration is 0. Is it looks like you have 3 pieces of information, but you really sort of only have 2. Another way to think about this is being given this information and then being asked to find t is sort of like you're being told this. I have an object. It's going 14 meters per second and it doesn't speed up or slow down. How long does it take to get there? And you're going, to get where? This is not a problem I can solve, right? Or maybe if you were being asked to find d, it's sort of like you're being told, I have an object, it's going 14 meters per second all the time. How far does it go? Well, I can't answer that. It depends on how long it drives for. So these three pieces of information are not enough on their own to find d or t on this side. So that's why I'm going to have to start on the vertical side. Let's give myself some more space to do these calculations. So, if I want to try and find t on the vertical side, I'm looking for an equation that has t but doesn't have vf. And I think the one that's going to fit the bill is this guy. Now, this equation, you might start, alarm bells might be going off right now because you might be remembering that this equation actually kind of sucks for finding t because I've got two of them, and because one of them's squared, it's really hard to isolate t. To put this in a form that says t equals. We can sort of do it with the quadratic formula, if that's something you know from math class, but that's a lot of work, and you might not know how to do it. However, in this particular case, in this particular problem, because vi is 0, down here in the equation where I have vi times t, it doesn't matter what t is because I'm multiplying it by 0. That whole thing I've highlighted is going to be 0. So this goes away because vi equals 0. So my equation becomes d equals 1/2 a t squared. And I can plug numbers in. D is -12. A is -9.8. D squared. And then if I solve that for t, I will get the t. And if I round this to 3 sig figs, 1.56 seconds. Okay. So then I can go and add this to my chart up here, if I want to. So I've kind of solved for part A. How long is the ball in the air for? That'll be 1.56 seconds. The next question, how far from the building is the ball when it lands? Well, that is basically asking me this distance here. Here's the building, there's the ball when it lands. I want to know how far those are away from each other. So that thing I've highlighted is the y component of this red vector d. What I'm basically looking for in part B is displacement in the, sorry, I said y direction before. I meant x direction. I'm looking for displacement in the x direction. So I'm looking for this guy. So let's look on the horizontal side here. Remember, although I didn't before, I now know time, because these two are the same, and I just found that one to be 1.56 seconds. So time on both sides is 1.56 seconds. So I'm looking for an equation that has d in it, and it's allowed to have anything else, because I know everything else at this point. So probably the one that's going to be easiest is this guy, because I don't have to rearrange it. And again, my life's going to be a little easier than usual here because acceleration is 0. That means this guy is 0. So it doesn't matter what t is, because I have a 0 in this term that everything's getting multiplied by, that whole thing is going to be 0. Zero because a equals 0. So d equals VI t. D equals positive 14 times 1.56, which gives me 21.8 meters. Positive. Okay, so that's the answer to part B here. How far from the building is the ball when it lands? 21.8 meters. That's this distance there, the x component of displacement. So now for the most difficult question of these three, what is the ball's velocity as it hits the ground? Well, we said it hitting the ground was final. So I'm being asked to find VF. But there's two parts to VF, a horizontal part and a vertical part. And I know the horizontal part, but I don't know the vertical part. So what's the deal here? Do I already know this answer? Is it just 14? Do I still need to find this answer because it's this one over here? Or is it something else? Well, it's something else. This doesn't specifically say the ball's x velocity or the ball's y velocity. It just says the ball's velocity. So what it's effectively asking me for is, one of these blue arrows over here. It's not talking about the components, it's talking about the full velocity itself. So as this ball hits the ground, it's going to be kind of moving down and to the right. It's going to be moving on a slant. It will hit the ground at an angle. And it's that angled velocity, that blue arrow from this diagram, that I want to know. So the way I'm going to find that blue arrow is by first finding these components and then adding up to get this blue arrow as a resultant. So to find the total velocity, that blue arrow, I'm first going to make sure I have these two components, and then I'm going to add them together. Okay, so I already have one component. I have the horizontal one. Now let's find the vertical one. So back over here on the vertical side, I want to find VF. So I'm going to say VF equals VI plus AT. VI is 0, and T, so VI is 0, I have that up here. T is 1.56, I found that down here. A is negative 9.8. So I get VF is negative 15.3. Okay, so that goes up here. That's my x component of VF, or my y component of VF. I also have my x component, and now I have to combine them. Combine that x component and that y component to get the full velocity. And let's do that kind of down here. I'll carve out an extra spot for this. So finding VF. Okay, let's draw this out. So I have an x component that's positive 14 and a y component that's negative 15.3, and I'm going to combine those or add them together. So an x component that's positive 14, so it's going to the right. and a y component that's negative 15.3. So it's going down. And this is going to be because this guy is horizontal and this guy's vertical. I've got a 90-degree angle there. And the resultant I'm trying to find, the combined velocity of these two components together, is that guy here. That is my VF. So I want to find VF. Well, it's a vector. That means it has magnitude and direction. I'm going to have to find both of those things. I think I can find its magnitude using Pythagoras and its direction using SOHCAHTOA. Let's give that a try. So, magnitude. I'm going to use a squared plus b squared equals c squared. C is the thing I'm looking for. So that's going to be equal to the square root. If I rearrange everything and isolate c, of 14 squared plus 15.3 squared. And that tells me that c is going to equal 20.7 if I round it to 3 sig figs. And now the direction part. Maybe I'll put my direction here. Got some space on the page down here. Let's do that. So I always define a vector's direction from its tail, right? There's an angle here near my VF, and there's an angle here near my VF. Which one do I choose? I always choose the one by the vector's tail. So I'm going to try to find this angle here. I'm going to call it theta. And I have to choose between sine, cosine, or tangent. Well, I know if I'm looking at theta, I know the opposite side and the adjacent side. So that means that tan is going to be pretty useful. Turns out I actually know the hypotenuse as well because I just found it over here. But in case I made a mistake somewhere in here, it's maybe wise to not use that hypotenuse in my calculation for theta. So I'm going to use tan with the opposite and adjacent side. Tan of theta equals opposite over adjacent. So 15.3 over 14. I inverse tan both sides, and that gives me that theta is equal to 47.5 degrees. So my velocity, remember I'm trying to solve for part C here. This is the final part of the problem. What is the ball's velocity as it hits the ground? My velocity, its velocity as it hits the ground, VF, it's a vector, so it needs to have magnitude and direction. Its magnitude is 20.7. meters per second. And its direction is 47.5. That's this angle here. And that shows my vector as being below this horizontal line by 47.5 degrees. So my direction is 47.5 degrees below horizontal. And that is my final answer. So, quick recap. When you are solving 2-dimensional projectiles problems, all this stuff as long as we have a horizontal initial velocity, which this first set of problems all will, all this stuff in green is going to be the same every time. We know, because the initial velocity is horizontal, that the y component of it will be 0. We know that acceleration is going to be 9.8 meters per second squared down, so it'll be in the y direction and it'll be negative. That's because we choose our initial and final, so that the entire time between those two, the ball is not touching anything other than the air, only has the force of gravity on it. We know that there's no force in the horizontal direction speeding it up or slowing it down, so that's going to be 0. And if it can't speed up or slow down, that means that these two are going to be the same. And since time isn't a vector, it can't be different in the x and y directions, so those two are going to be the same there. That's true every single time you do one of these problems with an initial velocity that's horizontal. Then it's a matter of filling in the things you know that are specific to the problem. In this case, it was these blue numbers here. Pay attention to whether things are positive or negative. And then it's a matter of picking your equations and deciding what side to work on to find what it is you're looking for. Be wary that sometimes it may look like you know 3 different things on this side, but you don't actually. Just knowing these first 3 is not enough to solve for anything else. So if you're in that situation, better off to start on the vertical side instead. And then finally, if the thing you're being asked to find is a vector, and you're not specifically asked for the x or the y part, like here, when we were asked for the ball's velocity as it hits the ground, that's a vector, and it didn't tell us just x or just y. That means you have to find the whole thing. So find both the x part and the y part, x part and the y part, and combine them to get the full thing, using Pythagoras and SOHCAHTOA to give a magnitude and a direction. That is everything I wanted to say about this lesson. Hopefully it made a little bit of sense to you, and good luck on the problem set.